So welcome to myself Dr. Santhosh Singh, working as an associate professor in Department of Physics, Institute of Aeronautical Engineering. So today I am going to discuss about occupation probability and carrier concentration. It is the part of semiconductor optoelectronic course. So let's start. So we already discussed about the density of state in bulk case as well as quantum well structure case, and we have found that in density of state in bulk semiconductor varies accordingly. Rho of E is equal to 1 upon 2 pi square 2 mc upon h cross square whole to the power 3 by 2 E minus EC to the half, where mc is rest mass, or you can say the effective mass of the electron in conduction band, and this EC is nothing but band age energy. Okay, we already discussed all these things, and in rho of E in valence band is equal to 1 upon 2 pi square 2 mv upon h cross square whole to the power 3 by 2 EV minus E to the whole to the power half, where EB is again band age energy in valence band. Okay, means top of the valence band energy, and this EC is bottom of the conduction band energy, means lowest possible energy in conduction band. Okay, that's why band age energy. So why I am discussing these things today? Because this density of state is very important for determining the carrier concentration. Carrier concentration. Okay, we already calculated the density of states in quantum well structure also. Quantum well structure. And we have seen that in quantum well structure, the density of state is constant. Okay, so definitely, if for determining the carrier concentration, if the density of state is will play the important role. So if its value will be constant, so definitely in quantum well structure, if its value will be constant, so obviously it will affect the number of available carriers for conduction in quantum well structure. So that's why again I am telling all these things. What are the expression? Okay, in density of state in bulk semiconductor as well as quantum well structure, and what are the variations? So see here, in bulk semiconductor, the density of state means rho of E is vary according to e to the power half in conduction band as well as valence band. So if you plot the graph of density of state for bulk semiconductor, so it will comes like that. Okay, rho of E, rho of E and E means you are taking the density of state at x-axis and energy at y-axis. So the density of state plot will be comes like that. Okay. Now, once you plot the, already I discussed this thing also. Once you plot the density of state for quantum well structure, what you will find? You will see, you will find that the density of state, that is rho kt for quantum well structure, that is the special notation for quantum well structure. This T represent the transverse component only. So that will be constant in particular region. Okay. So it will be looks like a step function. Okay. See. So why I am discussing this again? Because these density of state will play the very crucial role for determining the carrier concentration. Carrier concentration. Okay. So that's why I am again just giving the quick overview of all these things. So this was the density of a state. As I mentioned that the importance of this density of a state is to determine the carrier concentration, and we need to determine the carrier concentration to know the current. Why? Because why the carrier concentration is important? Because I always want to know how much current is flowing. Okay. So how you can calculate how much current is flowing, or it can be flow by knowing the available carriers. Okay. So for determining the carrier concentration, it is very important to know about the density of a state for particular material. Okay, which are which will be useful for device application. So generally in semiconductors, up to electronics field, the semiconducting material will be useful. So obviously we will give the emphasis over the density of state for semiconducting material. Okay. And we also try to find out or calculate the available density of state, and then after, based on that density of state, we will try to find out the available carriers. Okay. So now come to our main topic, carrier concentration. So carrier concentration or carrier density or charge carriers can be represented by N. This N is what? Total charge carrier available inside the material. Total charge carrier available inside the material. Okay. So these charge carriers, where it will be? According to quantum mechanics, they will occupy some levels. Charge carriers are nothing but basically electrons. So where the electron will reside? They will reside, or they will occupy the energy states E1, E2, E3. Okay. And available energy state per unit energy range, per unit volume is known as density of state. So how many these charge carriers are available in particular energy range? Okay. So that thing is known as NE. N of E means for particular energy, what will be the charge carriers will occupy that particular energy. And if you multiply with D, suppose this E1 and this E1 will contain, let's suppose, N number of charge carriers. So this NE represent the number of charge carrier. NE1 is now representing the number of charge carrier occupied in the level E1. Okay. Now, suppose you want to know the number of charge carrier between E1 to E3. So E3 minus E1, E3 minus E1, let's suppose is giving the some value D. So if you multiplying with this D means this energy range NE multiplied by D means if the single energy level is holding n number of charge carrier, then D energy range, how much charge carrier will be hold, you can calculate. Okay. So suppose there are up to E1 to En energy levels are available for providing the accommodation of these charge carriers. So, and you want to calculate the all the available charge carrier inside the material. So, what you have to do? You have to integrate this thing over lowest possible energy level to your desired energy level or highest possible. Suppose you want to calculate the total charge carrier inside the material. So even to En integrate over this thing Ne multiplied by D, integrate Ne multiplied by D over E1 to En, it will give the total available charge carrier inside the material. Okay. So this NEDE will provide the number of charge carriers in the energy range DE. And suppose you want to calculate the number of charge carrier for entire material or entire crystal, so you have to integrate this thing over entire available energy range. That's why this NE integral over NED will give the total number of charge carrier, and that is represented by n, small n. Okay, but we already told that the density of state is very important for determining the charge carriers or available charge carriers. So see here, this NED, you can write this NE. NE is what? A number of available charge carriers in particular energy E. N of E is what? Number of available charge carriers for particular energy E. So this Ne can be write as in term of density of state rho E multiplied by Fe. Okay. So this equation number 1 will turn into this form. N is equal to rho E Fe dE. Now what is rho E? Rho of E is density of state. Rho of E in the conduction band, rho of E in the valence band. Okay. And what is this Fe? This function Fe is known as probability distribution function of electron or probability of occupation. In other words, probability of occupation. Okay. The same meaning, probability of distribution of electron in available energy levels or probability of occupation of electron. Both have a equal meaning. So see here, your available expression for charge carrier inside the semiconducting material N is equal to integral over Ne dE is turned into the form of rho E Fe dE. Okay, means the available charge carriers for particular energy level is equal to the density of state multiplied by probability of occupation or probability distribution function. In actually, this is the statistical mechanic where we will try to find out the probability for happening the any incident. So what will be the probability of any particular electron so that they can occupy in particular energy? That thing is given by this probability occupation function or probability distribution function. And in other name is also known as Fermi distribution function. Okay, Fermi distribution function. So that's why this rho E means density of state, and this Fermi distribution function for electron in available energy range are, you can, in other words, you can say that there is a rule for distribution or for giving the position of electron in particular energy level. There is one fixed rule. That rule is known as Fermi distribution function for any electron. How the electron will be distributed in available energy states, and that thing is known as Fermi distribution function or probability of occupation, or simply probability distribution function. What are the probability for any electron to occupy any particular energy level? Okay. So multiplication of these two things, density of state multiplied by Fermi distribution function of electron, will give the carrier density or carrier concentration. Okay. So see here it is given that what is the form of this Fermi distribution function or probability distribution function of electron. So the form or expression of that distribution function is Fe is equal to 1 upon 1 upon 1 upon e to the power e minus ef upon kt plus 1. This whole thing, e to the power e minus ef upon kt plus 1, will be in denominator. Okay. So what is E? E is the particular energy level where you want to calculate the probability. EF is known as Fermi energy, EF, one fixed energy level. I will introduce this thing later. What is EF? EF is known as Fermi energy level. K is Boltzmann constant. And see, the temperature will also play the crucial role. At what temperature you want to calculate? Plus 1. Okay. So this is the form of Fe. Fe is equal to 1 upon e to the power e minus ef upon kt plus 1. This is the Fermi-Dirac distribution function for distributing the electron in energy level, available energy level. Okay. So that's why it is written probability distribution function for electron in energy level. So what is written here? The probability of occupation for electron is given by statistical mechanics, and that distribution function is also known as Fermi function, and the expression of that function is F is equal to 1 upon e to the power e minus Cf upon kt plus 1. And that same thing is also known as probability distribution function. So irrespective of your bands means valence band or conduction band, the electron, even let's suppose this is valence band and this is the conduction band. This is the band edge energy, means EC energy level. This is EV energy level. In between this EC and EV, some EF, Fermi energy level, will be hold. So I will discuss this. What is this here? So even in conduction band or even in valence band, the electron will occupy these levels. Actually, these are the band, and these bands comprises with number of levels, E1, E2, E3. These are not a single energy level. Here the number of energy levels are available. Okay. So how the electron will be distributed in these energy level will be given by this function, and this function is known as Fermi-Dirac distribution function for electron. Okay. So in both valence band and as well as conduction band, the electron will be distributed by this law. So the probability of occupation for valence band as well as for the conduction band is given by the above function I already told. And now let's suppose here some energy level E1 in valence band, here some energy level E2 in conduction band. Now you want to find out what will be the probability of an electron to occupy this energy level E1? So just what you have to do, just put in the place of E, you have to put E1. What will be the probability, irrespective of band, either it will be a valence band or conduction band, irrespective of your band choice, you have to simply put the energy value here. In the place of E, you have to put E1, E2, where you want to know. Okay. So the same thing is written here. If you want to find out the probability of occupation at the level E2 or E1, just put that energy value in this expression. Okay. And EF is known as Fermi energy and its value is constant for particular material. So now from what is the Fermi Dirac distribution function formula? Fe is equal to 1 upon e to the power e minus ef upon kt plus 1. Now let's discuss the situation at absolute temperature. What happened? What happened at absolute temperature? Absolute temperature means T is equal to 0 Kelvin. So if T is equal to 0 absolute temperature, I am talking about the absolute temperature. So what happened? Fe is equal to 1 upon, if T is equal to 0, then E minus Ef upon Kt. So if T is equal to 0, this Kt is equal become 0. So E minus Ef upon 0 means something infinitive will come. So e to the power infinitive plus 1 means what happened? E to the power infinitive 0 plus 1 means 1. So at absolute temperature, the occupation probability or probability of occupation is 1. And in statistical mechanics, you know that if the probability is 1, so the incident will certain. Okay, means the maximum probability value, maximum value of probability for any incident is 1. Sun rises in the east, it is certain thing, so the probability of that thing is 1. So what I want to say, if anything is certain, its probability will be 1. Okay. So now at absolute 0 temperature, the probability is 1. Means, and you know that at absolute 0 temperature, the all electron will reside or will be the part of valence band only. Okay. There will be no free electron. All the electrons are free. It will become freeze. Freeze in the sense they will be the part of only valence band. Okay. So if you are plotting the probability distribution function versus probability curve, what you will get? See here, probability of 100% means this is 1 at what? At energy 0. So up to this energy level, all the levels which are below this energy level will be filled by charge particle or electron. Okay, at 0 Kelvin. I am talking about 0 Kelvin case. Once you are start increasing the temperature, what happens? The probability in this case, in this region, will little bit decrease than 1, and here in this case it will be increased than 1. 0. Here at 0 Kelvin, absolute probability you are getting. Absolute means Here up to zero energy level means generally the all electron will reside in valence band, means zero or below the zero energy level. Normally we consider this region is valence band region normally. So all the electron will reside in this band. That's why the probability of occurring the electron in particular band, in particular region is 1. So I am not talking about any particular energy level. I just put the value t is equal to 0. And if t is equal to 0, we know that all the electrons reside in valence band. So once you are putting t is equal to 0, the probability distribution function will give the value 1. Means definitely it is certain that all the electron will reside in some region, and that is the region where the probability is 1 and the energy is 0 or less than 0. So in this whole region will be considered as the valence band region. Okay. Now start increasing the temperature. See, this curve deviated from this perfect rectangle, means something deviation happened, and here some probability occurs. Initially at 0, above this energy level, means above the energy value 0, the probability is 0, means no electrons here. Okay, and below are equal to 0, this all the levels are occupied. But once you start increasing the temperature, what happened? The curve, probability distribution curve is modified. Suppose this red one is representing for 150 Kelvin. So see, some level are here vacant, but some levels are here filled. Means electron is now moving from valence band to conduction band, and some states are available which are free inside the valence band above 0 Kelvin. Okay, and if you are increasing more temperature, this available vacant state in valence band region will increase. Okay. Now, what is the Fermi energy or Fermi level? What is the concept? So, Fermi energy is often defined as the highest occupied energy level of a material at absolute zero temperature. Fermi energy is often defined as the highest occupied energy level of a material at absolute zero temperature. So we already just now discussed about the case. What happened at absolute zero means once you are putting the value t is equal to 0, what happened? So we seen that all the electrons are occupied in valence band and there is no single electron in conduction band. So here the definition is Fermi energy is often defined as the highest occupied energy level. So at of material at absolute zero temperature. So in this previous case, the highest occupied level is what? This Fermi level is often defined as the highest occupied energy level of material at absolute zero temperature. So at absolute zero temperature, the highest occupied energy level is what? This one. Up to this level, the electrons are filled. So this level is known as Fermi level, E, and denoted by E suffix F, EF. Okay. So during the calculation, it will show the value. Sometime it will come here or here, means greater than the zero value will come. But we have to fix this Fermi level at 0 electron volt energy level. Okay, these values are in electron volts. So normally the Fermi level will be at zero energy, zero electron volt energy level. If it will be comes in 0.1 or 0.2, you have to fix it at 0 Kelvin, because at absolute zero, the Fermi level will be occurs at 0 Kelvin, 0 electron volt. Okay, so that's why in the previous case your Fermi level will be, by figure you can observe that you can correlate the definition and figure your Fermi level will be definitely this level. So Fermi level is often defined as the highest occupied energy level of a material at absolute zero temperature. In other words, all electrons in a material occupy the energy states are below the Fermi energy at 0 Kelvin. Okay, so we already discussed the concept of Fermi energy is crucially important concept for the understanding the electrical and thermal properties of solid. So this concept of Fermi energy EF is very important. Okay, for governing the electrical and thermal properties of any solid. And the Fermi level play an important role in the band theory of solid. In doped semiconductor material, P-type, doped semiconductor means either it will be P-type or N-type based on your doping substance or element. The Fermi level is shifted in valence band region and conduction band region. Okay, and the Fermi level is referred to as electron. The other name of Fermi level is electron chemical potential. So these are some fundamental discussion about the occupation probability and carrier concentration. In my next video lecture, we will try to uh, develop some more concept about these topics, means occupation probability and carrier concentration topic. Thank you. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.